Welcome to Khetz Tutorials, and in this video, I'll be remaking practice problem 6.4. So I did this problem previously, but I used a different method, and we are just going to adapt that method a bit, but overall, the approach to this is a bit different, right? So previously, I just did the area analysis, and before I even talk about the problem, let me just quickly read it. It says an initially uncharged 1 millifarad capacitor has the current shown in figure 6.11, which is this figure that we have here. And it says calculate the voltage across it at times equal to 2 milliseconds and time equal 5 milliseconds. So I have the summary of the question over here. We're interested in finding the voltage, and we know that I equals C dV over dt for a capacitor. Now the voltage is over there on this side, and to find it, now we just have to see what we can do. And what you can quickly do is just to do this, and you have this. If you integrate both sides, then this is what you have. And on this side, you can just divide both sides by C as well. And this will be your result. Right? So to find the voltage, when you are given current for a capacitor, you integrate your current and you multiply by 1 over C. So that is what we are going to do. We're going to use this direct method over here. And previously, I just did the area because your integral talks about the area below the graph. So in a way, we're still going to use that method, but we're going to compute the integral directly. So the times that we're interested in are 2 milliseconds, which is over there, and 5, which has to be somewhere over there. And now to find the voltage, we're still going to find the area under the graph up until the point which is mentioned. So for 2 milliseconds, it will be this area over there. For 5 milliseconds, it will be all of this area until we reach 5, including this portion of 2 milliseconds. So previously, I calculated the areas directly by using the triangle and the rectangle over there. But now I want to use this integral, and we're going to work with some integrals. So let's keep this formula in mind, and that is what we're going to use. Now to compute the integral using the formula directly, we have to find the formulas, right? So we have to find the formula of the graph, what represents the graph, so that we can actually put it in there in place of I and find the integral. So let's start with the first region. So starting with the first region, that would be between 0 and 2 milliseconds. Now in this region, let's find our formula. So that would be this line. We have a line here. We want to find its formula so that we can use it to find the voltage at time equals 2 milliseconds. So to do that, this is a straight line, and you know that a straight line follows this trend, and your m is the gradient. So you can find the gradient because it's a change in y divided by a change in x. And if you look at this point, which is still on the line, it has coordinates 2, 100. And don't forget that you actually are dealing with milli on both axes. So now we can just omit that for now because they're the same and they'd cancel out. So if you say 100, subtract 0, which is this point, the origin, 0, 0, it's on the line as well. And you then take the x value of that other point and subtract 0. Both of these, the top and the bottom, have milliseconds or milli as the prefix. So that will cancel out, and in the end, you just have 50. So this is 50, a constant 50, and you can substitute it back up here. If you do that, this is what you have. But in this case, we're dealing with t. So let's try to use t. Let's use t in place of x. And we have c. And c is the y-intercept when dealing with straight lines. And if you look at this, it cuts at 0. So we can just quickly say that this is our formula. So this is our formula for this region. So the triangle region from 0 to 2 milliseconds, we have a formula for this line here, which is that. So if we want to find the integral, or if we want to find our answer, which is the voltage, you'd now find the integral of this formula between these times, which are 0 and 2 milliseconds. And if you do that, we're going to say the voltage equals 1 over c integral of I dt. And we were told that the capacitor is a 1 millifarad capacitor. So that would be this. Milli is 10 to the power minus 3. And in the place of I, you'd put the formula of your current within that region. So we're dealing with this region currently. And within that region, our formula is 50t. Then we're going to find the integral of that between 0 and 2 milliseconds. I'm just putting this there so that you actually know it's milli. You can write it in this form. That's fine. Now, if you find the integral of this, we can leave the constants on the outside and only deal with the inside. And the integral of t, which is remaining in there, would be t squared over 2. And you'd now substitute your boundaries. And doing that, you then have the following. So you can simplify this on the outside if you want. And then you'd have to solve what's on the inside. So solving what's on the inside, you just substitute your upper and lower boundaries in here. That would be 2 times 10 to the minus 3 squared divided by 2. Subtract the other one, which is 0. And if you multiply this, then that should give you your final answer. So these are all the steps which are involved to find the voltage at time equals 2 milliseconds. Just find the integral. First find the formula, then find the integral of the formula within that region, and you should get your answer. And the answer we expect, or the answer that you'll get if you substitute this into a calculator, is 100 times 10 to the minus 3, so which is 100 millivolts. Don't forget your units. So that is what we have for the first part of the question. At time equals 2 milliseconds, right? And now that we have that, we can now move on to the other one. And the other one would be at time equals 5 milliseconds. And we do the exact same thing. We're now dealing with this region. And in this region, we then say that we want to find the formula of I. But if you look at this region, it doesn't just have one formula, because you have this point, then you have this a line which is like that. So we have to kind of separate these two into some other regions which have the same formula. So this region has its own formula from 0 to 2, and then from 2 to 5, that portion has its own formula as well. But we're in luck, because when dealing with integrals, if you want to find, let's say you have a point A and a point B and a point C. If you want to find the integral from A to C, you can find it by saying the integral from A to B plus the integral from B to C. So that is exactly what we're going to do. Because each of the portions have different formulas, we're now going to separate them. So we've already found the formula for the region between 0 and 2 milliseconds. That would be Y. If we want to call it Y, it's technically I, so we can say I, which is the current. And that would be I of t equals 50t between this region. Then we'd come to this other point, which we haven't talked about until this point. And between 2 and 5, it's a straight line. We have a horizontal line. And whenever you have a horizontal line, we know that we can assign that to just that value, because it doesn't matter where you stand on the line. you will still have that value. So whether you're here or you're there, as long as you're on the line, the value that you'd have is the y value at that point. And what will be changing are the x values. But it doesn't really matter anyway, because if you try to find the gradient at that point or across that line, you can choose any points that you want. Because the y values are the same, the y value will still be 100 milliampere. So you have an x value, let's call it x1, and another point that you pick on the line. Now, if you find the gradient of this, change in y divided by change in x, the change in y at the top will give you 0. And at the bottom, it doesn't matter what you have, the result of your gradient will just be 0. So this term is 0, and we just focus on what the y-intercept would be, or what we'd get at that point, right? And if you were to extend this so that it crosses the y-axis, it will just cross at 100, and that is why we basically have this. So that is your formula from 2 onwards up until 6 on the diagram, but we're only interested to get our formula until this point, because that is what the question is asking for. So it's just explaining how you get that formula and all of that, just so we're on the same page. So we now have 2 different formulas for these sections. This other section is actually between 2 and 5 milliseconds. And you shouldn't forget that this isn't just 100, it's 100 times. So this is the actual formula. This is the correct formula. I of t equals to 100 times 10 to the minus 3, because that is 100 milliamperes, right? And if you just use 100, it'll be totally wrong. And this is the formula in this region. Now, combining these two, we want to find the voltage between 0 and 5 milliseconds so that we can answer the second part of I dt. And we can do that by splitting the sections to parts that have the same formulas. So this portion has its own formula, and this other portion has its own formula. And the 1 over c can multiply all of them because it's common among both of them. So you can leave it on the outside, but it's fine. So now here we have a different formula for this. Then we're going to do that. Now this is between 2 milliseconds and 5 milliseconds. And we can close that. Now it's time to calculate. We still have the C as a 1 millifarad capacitor. And here we are going to find the integral. We can take the constant out once again. Then we can just deal with t, and we've already done this in the previous question. So if you want, you can just substitute the answer for the previous question over here, or you can just solve it again. So this is what we have. Then for the second part, you can take the constant out as well, and you're just left with 1. Now, if you find the integral of 1, you should get t, and you can do this. And close the big bracket. Now, once you have this, then you just have to substitute your boundaries, and you'd have this once again divided by 2. Then you'd have 0 substituted in there. Then you have a constant on the outside multiplying everything. And in here, you just substitute your 5 times 10 to the minus 3 because it's just t, and your 2 times 10 to the minus 3. You can go ahead and simplify this, and everything is multiplied by this on the outside. That is why we have that other big bracket on the outside. So you can go ahead and simplify this. Let's keep this on the outside for now. But in here, if you want to simplify this, this is what we did in the previous question, and it should give you the same answer. You expect to get the same answer. But since we haven't multiplied by the outside, then this is what you expect to get for the first part. And the other part, which is over here, you can also simplify before you multiply everything else. These have the same prefixes, and you can just focus on subtracting 2 from 5, and that would give you 3, right? Then don't forget your 10 to the minus 3. Now you'd multiply these two, multiply this and your 3 milli inside that part, and you'd have this as a result. And in the end, you'd have 1 over 1 times 10 to the minus 3. You can add these two, they have the same prefix as well. And this will be the result. And now all that you have to do is to multiply or to divide by 10 to the 3. So you either multiply by 1 over 10 to the 3 or you divide by it. And if you do that, then you expect to get 0.4 volts. So we're working with voltage, and you can convert this into this form, which is 400 millivolts. So that is how you solve such questions. When you're given an area, you find the formula for each section and you cover everything until the time that you're asked for. So everything until the time that you're asked for, and that applied to the 5 as well. We covered this whole section until we reach that point. So that is how you solve this question using integrals directly instead of just finding the area. So you can now choose, as I linked the other question, you can now choose which method you want to use for such questions.